Good day, greetings. So we are looking at electron configuration, okay? And we are saying electron configuration is the arrangement of electrons in an atom, molecule, or other physical structures. Now, you must understand something here. How do you form an ion? We form an ion when we lose electrons. When we lose electrons, we say we form what we call a cation. A cation is like sodium plus. Now, sodium plus, it means that it have lost one electron. It have lost what? One electron. Then we have got or magnesium 2 plus, it means that it have got lost 2 electrons. So it's minus 2 electrons. In this case, this one is minus 1 electron, minus 1 electron. Then it can gain to form what call an N ion. N ion is can be chlorine ion, like that. It means that it have got gain 1 electron. So it's plus 1 electron. That's what it means there. Then that's how your ions are formed. Now, an atomic orbital is where you find what you call electrons. So it's a region where you find what you call electrons. So an atomic orbital is a region in which an electron may be found in an atom. Sorry. Now, then let's look here. Pauli's exclusion principle. You need to understand this. It's saying an orbital can accommodate a maximum of 2 electrons with opposite spin, which means in opposite direction. So here we have got an orbital. Then we are saying it can accommodate 2 electrons with opposite spin, meaning to say it's facing different directions. So here we have what called two types of orbital that you need to understand for at your level is the s orbital and the p orbital. Now the s orbital, it accommodates only 2 electrons, only 2. Then the p orbital accommodates a maximum of 6 electrons, which means we have got a 2 plus 2 plus 2. So we've got the z, the px orbital, the py orbital, and the pz orbital. So in this case here, each of them, they accommodate 2 electrons. And you must remember, an orbital only accommodates 2 electrons. So that's what we have here. Then we are saying electrons, they are always in pairs in the vertical, in an orbital. Then this is your orbital. Fill the first orbital with the lowest energy. So whenever you are filling electrons, we are going to do it. You fill first the smallest orbital, which is the lower energy, which is the s orbital. So s orbital must be filled first, irrespective is it in the energy level, second energy level or third energy level, it must be filled first. That's your lower energy energy or lower orbital. Now then let's move on to hands through. You must know this name. You must know this hands through. Hands through, when more than one of the same type of orbital are available, which means the 3p orbitals, an orbital first receives 1 electron before the second orbital. So here you must understand something here. We are saying we have an orbital here, p orbital, and the p orbital accommodates 6 electrons. Remember? So this is the p orbital. So we are saying when you are filling in the orbital, let's say you are filling 4 electrons. So we have got 4 electrons that we need to fill in the p orbital, which accommodates 6. We are going to do this. We are going to put 1, 2, 3. So first of all, make sure that each of them receive. Then lastly, we put it here. Then we know that all of the 4 are fine. So we can tick and say this is our right. This is what you're supposed to do. You mustn't do this to say, let me fill in the first. Okay, let me fill in the next. Then in that case here, we are saying this is a no. This is a no. You must not do this. You must always remember that. Then here, let's look also at affable principle. So you must be able to state the hands through, then also affable principle. The orbital with the lowest energy level filled first. So here we are saying always the s orbital must be filled first. So the one with the lower energy. So let's give an example of sodium. Sodium 23 and 11. So here we are going to look at the what number of electrons, which are 11. Now we are saying electron configuration is represented by orbital box diagram, or what we call electroscopic notation. So we're going to start with the first one for what we call for sodium. Now we've got 11 electrons, and what do we know now? We know that in the first what we call first orbital, this is the s orbital, 1s1, the first energy level. We've got the second energy level. Let's see here. First energy level is filled with the 2 electrons, which means we only have the what 1s orbital. So it's 1s2. So we're going to fill in 2 electrons there. Then you got the second energy level. In the second energy level, we know that we must have what? We must have two s. We've got 2s electron, 2s orbital, which is so we must can fill it in, because we have 4 and we are remaining with 7. So here we go on again and say, all right, what about the p orbital? The p orbital, we have the p orbital here, and the p orbital accommodates 6, and we know that it's going to be able to fill in all this. Now what do we have here? We say 2p6. Now we have got first. So we've got 6 now. So in the second orbital, we find that the first orbital, how many are there? There are 2 electrons. Then the second energy level, there are how many? 8 electrons. So that's why we are saying it's what 8 electrons is, because we have got 2s2 plus p6. Then the 6 plus 2, it gives you 8. That's why you must always remember in each where there is s and p except the first energy level. Now here the third one, we find that we're just going to be able to fill in the s orbital only, the s orbital, which is going to be 3s1, because we are only remaining with 1 electron, which we'll put here. So this electron here we refer it to as what called valence electron. Valence electron or outer electron. This is the one that is used in the chemical bonding. I mentioned that also before, in the chemical bonding. So this is the one that is used in the chemical bonding. This is the energy that the electron that can be lost, can be shared, they can do anything with it, isn't it? This electron is free to, can actually live there, but for bonding and everything. But the other electrons, we refer them as to core electrons. So these core electrons, they are not what you call active. They are not active. They don't move around. Now, that's what we have as the what you call orbital box. So that's what you do when you're drawing the orbital box, what you call diagram. Then let's look at the second method, which is electroscopic notation. Electroscopic notation, we know that the first, we're just going to write S2. Then we have got the 2s2 again. Then we've got the 2p6. Then we have got 3s1. That's how you represent what you call the electroscopic notation. So you must always remember to differentiate the two. Then here we also have the third method that we call the shorthand electroscopic. I'm not going to finish it. Electroscopic notation. Now, in the shorthand electroscopic notation, here we are going to use what you call the noble gases, or what you call the inert gases, what you call the inert gases. And when we look at sodium, how do we put it? Sodium, we know that sodium 11, we know that is, where is it close? Is close to where? To what you call neon. So we're going to say neon, and neon plus what we have 3s1. That's how you put it, the shorthand. And if we are to refer to lithium, we have got 3 what? We have got 3 electrons, and in this case we're going to put helium, which have got 2 electrons, helium plus the 2s1. That's what you're talking about there. So in total there, you find that if you have to add here, we say 10 electrons that are in the what on the neon, plus 1 electron, then give us sodium. So that's what you must always remember there. Then let's look at what you call ions. Now, how do we write the what call the what call electronic configurations for ions? Now, in this case here, this is something that they have lost electrons, like sodium, sodium, we know that sodium plus. So sodium plus, it means that it's no longer having 11 electrons, it have got now 10 electrons now. It have got 10 electrons. Now, when you have got 10 electrons, it have got an electronic configuration of what? Of neon. And the neon is actually stable. It's stable because there is no free electron, what called, there is no valence electron. They actually, the valence shell is filled. The valence shell is filled. It means that here, if you are to put the what called the configuration, it's going to be 1s2, 2s2, and 2p6. So it means that we have got 8 electrons in the outer shell in this case. This is what call what is it what is it an ion for sodium. Then wait, let's look at for chlorine. Chlorine, because it have got we have got an extra here, and chlorine must have 17 electrons. It must have 17 electrons. So in this case here, they are now 18 electrons. They are now 18 electrons. So in this case, when they're 18 electrons, it have attained a what you call a stable state of argon. So it's now an argon. Now, when we have got argon, what do we do with 18 electrons? We are going to write 18 electrons. We're going to say 1s2, 2s2, 2p6, then 3s2, 3p6. Then if we are to add them, we need 10 and here 18, and it's actually stable like this. That's what you must always remember when you're dealing with what called ions. This is the electronic configuration. I hope that was helpful. Thank you so much. Until next time. So you can also ask for notes. There is no problem. You can request on the number that we have there, Emerald Private Tutors. Okay.